Oh, I turned on the mic, then I moved it. Hold on, let's unplug the mic for a bit. Okay, cool. I think I have fixed my microphone. Woohoo! Alright, everybody hear me? Am I loud enough? Am I too loud? Is everything working? I think everything's working. Oh, I also think I still have the music playing, don't I? Yes, I do. Let's turn that off. Actually, maybe I'll leave it on. Just make it like really quiet. Kind of like that, you know? Is that quiet enough for it to be non-distracting? Alrighty. Let's turn the... There we go. Okay, so Michelle, I know I just sent out the link to the Google Drive like an hour ago, and I don't think anybody's posted to it. I don't think so anyways. Let me check that real quick. No, nobody has posted to it. That's fine. I think the music is mumbling my voice. Okay, okay. Can I... Okay, I'll just turn the music off then. That's probably better anyways. I have so many windows open, it's crazy. Okay. I got my coffee, got my microphone and everything works. I think that we are ready to go. So how are y'all? Alright, so... Okay, so like I said before, I don't think anybody's posted anything in the Google Drive. So yeah, if you have any specific questions, just post them in there. Oh wait, no, nobody's posted anything. Or let me know if you maybe like didn't get the email or something like that. That could also be a thing. Or if the link doesn't work, right? Screenshot, just take a screenshot, take a photograph of the problem. Everything's cool, doesn't really matter. In lieu of that, I suppose we can go through the rest of that worksheet from Thursday, right? Because I don't think we got to a whole lot of it. Can I go over a past exam? Yeah. Okay, so let me... Well, that's my Twitch stuff. Let's go to here. I'm just gonna drive you through my Google Drive. Hopefully nothing sensitive comes up. Let's see, organic. I Actually, I should probably just do this on the separate screen. But whatever, I'm daring. Let's see. General collection? I have no idea where I put this stuff. Yeah, Thummel test. Thummel test 3. Do I have any Dr. Bean stuff? I don't think so. Orgo test bank. That's probably in that folder, isn't it? Organic 2, Orgo test bank is promising. Exam 3. Okay, so I noted at the beginning of like the semester I don't really have any exams. I don't. All I have is test 3, test 3, test 3 final, test 2, test 3 finals. I don't know what happened to my other exams. But anyways, test 3, let's do maybe 2009. Oh, that one has the answers already. That's not fun. Here, I should really do this on a separate screen. Is it possible to create a cyclohexane? So, create cyclohexane. While I'm thinking about this, I'll keep looking for another test. With OH and BR substituted on the same. So OH and BR here. That is our our thingy. I don't know. Is that possible? It would be very pH sensitive, I would imagine, right? Because if you put this in any any sort of like basic, right? So like pH, that should be a capital H. Not that it really matters. pH below 7. Right, so the alkoxide, I'm just trying to think of like would it be stable enough to mess with, right? That would immediately come down and kick that off and just form cyclohexanone. So it's not stable in basic. Is it stable in acidic? Or is stable in neutral? Is it stable in neutral? That can come down and kick that off. Yeah, I reckon it's possible. I reckon it's possible. I just don't think I've never quite seen that. It's not very common. I'm sure it has some stability issues. But sure, as far as how to create it, that's a good question. Or that's an interesting question. Let's delete all this stuff. Well, PDF annotator is really slow at highlighting. It's really struggling. Just stop. Just stop it. Okay, well, I'll let it do its thing. I put a link to all the past exams on the Google. That's very helpful. That makes a lot of sense. Okay. As far as how to make... Ooh, voice is going there. As far as how to make this, I think... I mean, because you could not just... I don't think you could just do this. Oh, I just drew like 3 circles. And then like a BR minus... Because this would... That couldn't happen, right? That's not nucleophilic enough. You would need an OH and the BR to be added. Maybe with oh, I got an idea. Assuming that there exists some conditions where it's stable, that is. Starting with a triple bond and then reducing it to a like a vinyl bromide. Maybe. Looking for my selecting tool. I just want to erase this. And that's going to take a while again. Okay, I'm searching through the Google Drive. Trying to do a million things at once. That's fine, though. That's fine. Marked. Cool. Oh, it's a Dropbox link. That's okay. Okay, well, I got some questions from an exam. Oh, good. Switch back to here and then just delete. There we go. As far as how to do that, I don't think it's possible with the reactions we know so far. The only thing I could possibly think of would be to get a triple bond, reduce it to HBr. Oh no, I guess you'd have to use OH. No, I don't think that's possible. Not the reactions we know so far. I don't think that's possible. To get an alpha substituted bromine like that. Yeah, I don't think that's possible. But if you can find a way to do it, go for it, assuming that it's stable. Right? The big kicker with this would be really useful if you can get a triple bond and then somehow get an alcohol. But again, that alcohol is not stable, and then get the bromine on here. Right? Or take this and get the bromine and then get the alcohol. Right? So the issue with either of these is this right here is not stable. Right? This would get reduced to a ketone. And this, to get this one, you need HBr, and you wouldn't be able to stop at the double bond here. You had to get two bromination. So no, I don't think that's possible. But it's an interesting question. Okay. So I got this question on the Google Drive. It is from a test, it seems like. So I will consider that as going through a test. Let's go through this. And I wish I could just like, can I? Oh yes, I can click and drag. Awesome. Actually no, I figured out a cool way to do this before, and it's through the magic of technology. Right? If I just open that up and download it, and I can just like click and drag it into the PDF annotator. Nope, that's not the right thing. Downloads. Oh gosh, so many stuff open. So much stuff. I can English, I swear. Alrighty. And click and drag that. And maybe zoom out a little bit. Whoa, that's a whole page. Let's maybe Control X. Yep. And then page. Insert page. Nope. Append page. Append. Yes. V. There we go. I know how to use technology. I'm smart. Okay. So let's go through this. I'm not gonna be able to like erase anything, because I would erase the entire picture, which is unfortunate. Oh, please. Okay, there we go. That's okay. Okay. So let's go ahead and get started. Then we'll move on to a test. Or I know actually a couple other questions popped into the Google Drive just as I got this one out. So that's nice and dandy. Okay. So it says place the alcohols in order of increasing reactivity with an acid catalyzed dehydration. Okay. So acid catalyzed dehydration, that's just simply alcohol H2SO4, right? So an anhydrous acid, and we're forming a double bond. So I guess as a little like side scratch work here, right? If you recall, the way that mechanism worked is we went from the alcohol. I'm not going to do the full mechanism, just kind of do like a pseudo mechanism, so to speak. Alcohol, the sulfuric acid protonates it, right? and then it leaves. So one of the things that we're looking for in this is carbocation stability, and that's probably actually going to be the only thing we're looking for, thinking about it. Right, and then after that, it's just easy peasy. Something comes in and E2s that hydrogen. Right, so I have a highlighter because technology. Right, so this is the thing that we're looking for here. Carbocation stability. So if we make a carbocation here, this is too far away from that double bond to resonate, but that is secondary, which is okay. Right? If we make a carbocation here, it is also secondary, and it resonates. Yay, resonance. Right? And if we make a carbocation here, it is primary and no resonance. Right? So reactivity-wise, this would be the most reactive. And recall that carbocations are more stable on higher order carbons. So go back to the pen. There we go. So this would be 2 and this would be 1. Yeah, I think that works out. Okay, let's go down a little bit. Okay, so it says place the compounds in order of increasing acidity, right? So 1 is the weakest acid, 3 be the strongest. Okay. So as an acid, we're having some compound and we're deprotonating, right? It's giving away a hydrogen. So what we want to do is we want to identify the most acidic hydrogen on each of these, which is going to be the oxygen, the nitrogen, and that carbon right here. Deprotonate it and look at the stability of their anion. Right, so that'll give us a C minus, or triple bond C minus. So O is some alkoxide, that's fine. And then some amide. Okay. So as far as strongest acid goes, maybe I have to do a bit of guesswork here. Don't know off the top of my head. We can kind of say to begin with that the O, just by like electronegativity wise, this is my first guess at that. Just by electronegativity alone, because we don't have any resonance, right? That negative charge is not resonating. We don't have any resonance, so I think it's just based on electronegativity. There is something here with like sp character going on, but I don't think it surpasses the nitrogen and like pKa, so to speak. So this is my first guess. Right, does that sound right to y'all? I'm going to get my textbook really quick just in case I have to reference anything. Grab the wrong textbook. Alright, got my textbook. Now, so your textbook actually has like a pKa table in the back. So if you're having trouble looking for like definite answers on these things, it's always very useful. No, I actually forgot where it is. I want to give you all like a for sure this is right answer on this. So, do you know how it goes? Alright, just want to go to the back. Appendices. Those are study problems. That's NMR. That's not quite what I'm looking for. No, that's spin. That's still NMR. That's IR. Anybody in chat? Nope. Well, when in doubt. Oh, what? I found it. Okay, so according to, I almost wrote on my book with my digital writing pen. According to the textbook, terminal triple bonds. Let's see here. That's iodic acid. Terminal triple bonds. Where on earth are they? I would say pKa of about 25, right? So remember, the lower the pKa, the better, right? For alcohols, oh, I see what you posted in chat. Key says for this 231. Okay, so the sp character somehow outmatched the nitrogen. Okay. Looking for amides. Now I'm just kind of curious to see if it actually matches up with these pKa's, but I suppose. Oh yeah, this is about 40. Right, so pKa for amides is about 40. Yeah, so that's quite a big difference actually. Wow. Right, and just for reference, I suppose pKa for this triple bond or for the double bond is about 44. That's very interesting. Right, and for alcohols, I think we all know that alcohols are the most acidic out of all of that. But just for completeness, we can get the pKa. Looking for alcohol. Hey, it doesn't matter. That's phenyl. Nah, don't care anymore. Okay, so yeah, so this pK for double bonds, it's 44. Yeah, so actually for terminal triple bonds, this hydrogen is quite acidic actually. So that's interesting. Yeah, so I know this has to do with like sp character. I didn't actually know to the extent of which this like happened, but it's quite drastic actually. Changing that much. So as far as okay, so I guess I should explain what sp character is. Let's go to a new page and do that. Right? Append the page. Okay, so if we want to compare like double bonds, now this isn't gonna really help us compare triple bonds to an H, but it is gonna help us kind of understand why. Okay, so it's a question: why are terminal triple bonds acidic? Right. So this hydrogen right here is in a hybridized orbital, right? In an sp orbital. And so just a brief refresher on what that means. So when, according to like the Vespers theory of how molecules form and whatnot, when a compound forms a bond, right? Like for example, our good old neopentane here. This carbon in the middle here is sp3 hybridized, so that carbon mixed an s orbital, right? The electrons from an s orbital, and the 3p orbitals it had available to it in like that second energy level, right? Right, so it mixed together s and 3p's, and that has an influence on the way that this orbital is shaped, right? Like it's kind of a lobe shape like the p orbitals, but it still kind of goes back into centered around the center here like the s orbital is, right? So it's like 25%, so to speak, s, and then the rest of it 75% p. Right? Now if we the s orbital is smaller and holds the electrons like closer to the nucleus, right? Holds electrons closer to nucleus, right? Which in terms of energy is good, right? Because you want your negative charge to be as close as possible to your positive charge, right? As far as like potential energy goes. So the more s character, right? So another like %s, the more stable a negative charge, right, will be. Right, so comparing the neopentane, so actually that doesn't have a hydrogen to do, but let's just do that one, right? So comparing that acid to that acid to this acid, the pKa's should go down, right? And that's because like this triple bond right here is half F or half S character, right? So as far as an orbital shape goes, it looks a lot like an s orbital, right? Not so much that it doesn't look like a p orbital still half s and half p orbital, but it's compared to the other hybridized orbitals, it holds its electrons much closer to its nucleus, right? So now we can directly compare that to like a double and a triple bond of the same atom. But what the problem was asking us to do was to compare it to other atoms, right? So like looking at electronegativity is an obvious question, but then at what point does that electronegativity effect give way to this S character thing, right? Because so far we've really been only comparing sp3 hybridized stuff. So back to the problem on here, as far as a way to attack the problem, let's change color so we know what we're talking about here. We can kind of right away identify this is an acid, right? And usually when we talk about acidity, acid-base reactions, ammonia is a base, right? But normally when we classify it as more of a base, and that's really because it has such a high pKa, right? And of course, an alcohol, just because it's an oxygen, and oxygens are very electronegative, it kind of just overrules the triple bond, the sp character from that, right? So, right away put the 3 there for the OH, and then I guess I should correct that now, right? And that gets, nope, that's the wrong number. That gets the 1 because it's the only thing here that's a base, and then this gets the 2 because it's, in the middle. Yeah, when I first saw the problem, I knew this was acidic and it has sp character, but I wasn't sure at what point does it, bridge the gap between comparing to other atoms. Okay, I'm gonna take a sip of my coffee and wait for my stream to catch up. Let me know if that made sense. Oh, and as a reminder, so in case you weren't here last time, once I close down the stream later tonight, the video will be immediately posted to Twitch. If you go to like the second tab above the video player, there's like a videos tab. Just a quick warning: whenever you exit and re-enter the stream, you'll have to watch an ad. So it kind of sucks. Even I have to watch ads, even though it's my stream. But whatever. So if you can just make a new tab, it works just the same. And I'll post this like PDF file on Blackboard so you can look at it. Okay, so let's carry on. I'm gonna switch colors. Need to do this purple color. Yeah, purple. Okay, so here we're just ranking them in order of increasing acidity. Right. We're looking at all alcohols, which is fantastic. Right away, we can say that this is the strongest one because resonance. Right? If we deprotonate that, that's going to resonate back and forth here. Right? Now, between this one and this one, if we deprotonate this, well, that's just that. Right? If we deprotonate this, the question is, how is that fluorine going to affect that compound? Right? Recall that fluorine is a very electronegative atom. So what it's going to do is it's going to pull, create a very strong dipole moment along this bond, making this one slightly positive, slightly negative. That is going to pull by induction this electrons from this carbon, kind of like a giant tug of war. It's going to try to neutralize itself. So this is now slightly positive. And then that is going to tug just a little bit that way. Right? So this fluorine, through induction, is going to help to spread out the electrons. Right? It's going to help to delocalize the electrons on that oxygen. Right, so the fluorine is actually helping out with the stability of that anion. Right, so then that would be the 2, and that would be the 1. Yeah, just a normal alcohol would be the weakest acid. That one was significantly easier than the previous problem. Right? Okay. Let's carry on. Right? So it says, number 4 says, place a Y in the box below any halide that will produce a useful Grignard reagent. Right? Grignard. Place a no next to any box that will not. Okay. So here's where we kind of just plaster things about Grignard, right? So thing about Grignard, or Grignard, as the French decided to spell it, it is a very strong base, right? Very strong base. We're essentially making like a C- compound, right? So therefore, no acidic allowed. Right, no acidic hydrogens allowed. Right, so NH no go, OH no go, terminal triple bonds no go, so on and so forth. I forget the rest of them. But if we look here on the first compound, that's an NH, right? That NH right there, that's a no go. So that's a no. Right? Everything here looks fine. The nitrogen does not have a hydrogen on it. Am I thinking about that correctly? Yeah, the nitrogen does not have a hydrogen on it, so it's still okay. Right? So that's a yes. Right? It would be making the MgCl right here. Right? So that's still okay. Over here would be making the MgI right there. That's the Grignard we're making. This is an ether, which is not an acidic hydrogen. It's right here, not acidic. And none of the hydrogens on the benzene are acidic either. As a rule of thumb, we haven't really talked about benzene and the reactions of benzene. That's all Orgo 2 stuff, so we just kind of assume that it won't mess with stuff right now. It's perfectly fine. So anyways, nothing wrong with this. It's perfectly good. Okay. If we look at this one, we'd be making the MgCl right here, right? But that's an acidic hydrogen, right? Actually, I love the way that Dr. Bean kind of does these questions, because if you knew how to answer this question up here, you know that this hydrogen is acidic. So you can kind of use that over here to say, well, that hydrogen's acidic, right? That's no bueno, right? So that's a no, right? The next one, right? Pretty much the same thing. BRMG, right there. This is not a terminal triple bond, so that's perfectly fine. Oh, I don't have any acronyms for them. I just kind of look at them, right? I suppose you could kind of make an acronym. I'll leave y'all to do that. Okay, and this last one, scribble that out, MGBR. Right, none of these we actually learned before. Oh, yeah, these are definitely not acidic, not acidic, not acidic, not acidic. Right, so that's perfectly fine to do. It's actually a good way to make vinyl carbons. The more you know. Right, so just to recap that problem, the thing you needed to know is that Grignard is a strong base, so you can't have any acidic hydrogens. Right, that's the thing to know. Alrighty. Okay, I think that's the end of the problems from this page. Let's see what else has been posted in the Google Drive. Hit the refresh button, you know? Okay, well, it looks like I just straight up have a test. All right, let's do that. It's a PDF. That should be fine. In fact, what I'll do here is I'll exit that. Wow, I've made a mess of that, haven't I? So many colors. Let's save that. And I should have just downloaded the test. The key says the middle top should be no. Middle top, so this one should be a no. Well, okay, let's think about that one, right? Where is the acidic hydrogen? Trying to make it right there. So that one should be a no. I'm gonna load up my the test that I just downloaded, and I'll think about it. Because RMGX reacts. Oh, of course. Yeah. Right. This group right here is basically a double bond O. Right. This is an electrophile. So it would just come in. It would polymerize. Right. You'd make a big mess. Let's go down to the new page and point that out. Okay. So I went down to the new page, but I didn't. Scroll. Scroll is so big. Okay, got a good look at that compound. Okay, so we had like this compound, right? So if we make MgCl here, right? Double bond O and double bond N, and whatever else is on the N. Both of these are electrophiles, right? Like we know that your Grignard reacts with that, reacts with your ketones, right? Because the carbon here is an electrophile. It'll also react with these, and notice how similar the structures are, right? It's just double bond something to an atom that is okay carrying a negative charge, right? Obviously, oxygen is better at it than nitrogen is, but nitrogen is fine, right? It'll, like, this is an okay thing to have. Namely because this is still more stable than the Grignard. Right, your Grignard is a really strong base, and although the N minus is also a very strong base, your Grignard is stronger, right? So what you would have is N minus MgCl is a like counter ion, and then this carbon, so this carbon right here would have been attached. Let's switch colors. This is kind of cool to think. It's kind of weird to think about, right? So that is a new bond that's made. And let's switch to maybe a blue color, right? So this carbon would have attacked another compound. Not like on itself, because it would make like a triangle, and that's weird. But you have like a whole bunch of these, right? So it could attack another one of these. Right, and that's this. The orange one is the new bond that your Grignard made, and then of course there's nothing keeping like another Grignard, another one of your compounds that you just made, from adding onto that. Right. Let's see if I can do this. I don't know if that green is too light, but we'll see. Right, and that's a new bond made, and then that got erased, and then minus charge MgCl is a counter ion, right? So because you can react with like other compounds of the same type, and you have a big mixture of them because you're in solution, right? You can start this like chain and polymerize, and you just get a big gulpy mess, right? So you'll get polymerization. Polymer. Right? So as soon as that forms, it'll happen, basically. Okay, yeah, so that one should be a no. Okay, so this is new bond form. Yep. Good catch on that. Thanks for fact checking me. It's kind of late. It's the end of the weekend. Okay, so let's go through one of these tests. All right, see, okay, good. I'll open it up in a new tab. Yay! So there's the test, right? 2013. That's the year before I took Orgo. Let's see, can I get a nice big pen, right? Stream. Yay! I forgot what tip I was. There we go, that works. Maybe I'll go with the thinner tip. Yeah, that works. Okay, cool. Let's scroll down. Have y'all ever been tempted to put 100 right here? Just to start it out, you know? Like, they have it there. Don't do that. Okay. So let's, we have time. There's no rush here, except if you want to go to bed before, to go to school tomorrow. I guess there's a rush. But we can go through nomenclature, so we don't go through that in a workshop. Okay. So here, so the functional group, we have an alkyne. Let me zoom in. There's no. Actually, I want to go into that full screen mode, right? There we go. Beautiful. Right. So we have an alkyne. So we want to make the longest chain that includes the alkyne. So I'm thinking 1, 2. Wait, I can use the magic of highlighters. 1, 2, 3, 4, and through here, like that. Right, so that's the yellow one. Right, so how many carbons does the yellow one have? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon. All right, let's test another one. Maybe in a green color. Like this bottom one right here. 1, 2, 3, 4, 5, 6, 7, 8. Ah, well, of course it like corrected me there, but whatever. Okay, this also has 8 carbons. Right, and obviously if we started from right here and counted, that'd be the same amount of carbons. So now we have to go by most substituents. Right, nope, most subs. So if we go down the yellow route, we get one substituent. Oh, change colors because I can. Gotta take advantage of these things. Okay, so the yellow one would be orange, circled in orange, right? So 1, 2, 3. 3 substituents off the main chain. Right? And if I change colors here to like this green color, oh, that gets a 3. There we go. The green route has 1, 2. Right? So then the yellow route wins. Hooray! So we have identified our parent chain. Right, it is that one. Okay, so we have a methyl here. We have 1, 2, 3 with a propyl. We have methyl. Now, when we're numbering, we want to give the triple bond the lowest number. So if we start from here, 1, 2, 3, 4, 5, 6, 7, 8, I believe that'll give us the lowest number, right? Because if we went to, so this gives us a 3, right? A 3 here. If we go the other way, we get 1, 2, 3, 4, 5. We get a 5, right? So that, going from left to right, is the lowest numbering. So we have 2, 7, dimethyl, 5 propyl. I'll rearrange it later, right? 5 propyl should go first. And then we have oct 3 ine. Right, so now we write that up in the box. Alphabetical order, we ignore the die. Does M come before P? E, F, G, A, B, C, D, E, F, G, H, I, J, K, L, M. M comes before P. Yes, I had to go through the entire alphabet in my head. That's fine. Dimethyl, 5 propyl, oct 3 ine. Okay, and then last thing, check for stereochemistry. We don't have any stereochem for triple bonds, and none of the carbons are indicated with chirality. So woohoo! No stereochem for us. Easy peasy. Okay, can I like turn off? Oh, I can turn that off. Okay, good. I can actually turn off the snap to straight line feature. Okay, so for this next one, we're gonna start from the right over here because it'll give us the lowest number on our triple bond. We can kind of get that out of the way. So if we go from here and then go up, it'll give us a longer route, right? Because if we go up, it'll give us an extra carbon, right? So I want to go that way. So there's our carbons. 3, 4, 5, 6, 7, 8. We get oct 2-ine, and then we just have this ethyl here. Alright, so this one's actually it's pretty easy, right? So it's 5, and no stereochemistry to speak of. 5 ethyl, oct 2-ine. No stereochemistry, just that ethyl group. Yeah. Okay, so this one says number 2, and then the next one's number 4. Cheat hacks. Hey, now wait a second. That's Orgo 2. Oh, I went to the next page. That's Orgo 2 right there. That's a benzene ring. That's a benzene ring. We don't name those in Orgo 1. Let's go, Rana. Messing up. This one's for Orgo 2. Alright, this is a benzene. I think that's like the most dangerous thing about doing these tests from other people is, you know, sometimes they might include stuff from Orgo 2 if they're editing these tests, right? Okay. But what we can do, I guess to make it more relevant, if I take my little white marker and just erase those double bonds, then suddenly it is back to Orgo 1. Oh, no. Please erase. There we go. Now it's a useful question. Alright, let's get out of this white because it's really hard to see where I'm at. Let's go back to purple. I really like the purple color. Right. And we could make this a lot more complicated, like if we add a stereochemistry here, that would be a little more challenging, to say the least. But let's not do that, right? So as far as parent chains go, we have an alcohol there, and we have a triple bond. Remember, alcohol takes priority, right, out of all of the functional groups we know so far. So not only is it just a cyclohexane, this is cyclohexanol. And in fact, we can say 1-ol. Now, the 1 here isn't strictly necessary, because if there's only one alcohol, it has to be on the first carbon. But, you know, it doesn't hurt as a parent chain. We can go clockwise or counterclockwise. So we just have a benzene, and let's name both of these substituents really quick. Right, so this is ethyl. this is 1, 2, 3, 4. So this is bute 1, 2, 3. 3 inyl. I think that's how it is. Oh, we talked about phenyl in class. Did y'all talk about naming phenyl? I mean, because this is like well above phenyl. That's an interesting thing. Maybe I should stop editing the tests, right? Oh, regardless, I'll still have to name these substituents. Alright, so if you keep with the original thing, this is just phenyl. Or phenyl. Everything else still holds for what I've been saying so far. For phenyl, the 1 is still on wherever the alcohol is. And by the looks of it, this is going to be a B and an E. So this will be number 2, 3, 4, 5, 6. Okay, well, if she's talked about phenyl, then maybe I should stop editing the questions. There we go. I'll keep that the way it is then. Silly me. Imposing the things that I think I know. Right. Phenyl. These substituent names stay the same. So this is 1, 2, 3, 4, 5, 6. So we get 2 bute 3 inyl. I don't know if that E is supposed to be there. And then 6 ethyl. So instead of a ethyl group, we have an example with CH3, which is number methyl. Is it like 2-methylphenyl? There's a quick way to get these things. So let me bring that back over here. So let's go to UH library. This is what I do when I have nomenclature questions. I go to here. I look for SciFinder. I sign in, my super secret thingy. Right? Is it one word? I think it's one word. Yes, SciFinder. Okay, so we want to look at this database. Must register. Yeah. Login. Yeah. Go here. I swear I know what I'm doing. Very good. Yep, remember me. Go in. Okay, so this is one of these things that you have secretly been paying for as an undergraduate here, but you've never been told that you have access to. So this is a website you can use to like look up research articles and reactions and stuff like that. What I'm going to do is I'm going to type in 2-methylphenyl and see if it gives me the compound that I want. If this would load. To be fair, I guess I am streaming. Hold on. Alright. It's 4, but because we assume OH is first, right, and we count from there to determine the number. Right, absolutely. So, and is the example 2 ethyl phenyl. Let's go back to the PDF annotator. So is this example 2 ethyl phenyl? It would be, right? So yeah, so we definitely have this as a 1. And we have to make a choice, like, is this the 2 or is this the 2? Right? So so I named both of the constituents, and because they have the same numbers, right? Like either way, it'd be a 2-6 and a 2-6. Then we just go through we go by alphabetical. So because the B here comes before E, then this one gets the number 2. I should probably be writing in a different color. Right, so this carbon right here is the number 2. And then you continue numbering about, right? So it'd be 2 but3-inyl, or whatever substituent that is, and then 6 ethyl. Do, 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 do. Do, do, do. Okay. But yeah, if this other group right here wasn't here, then it would be 2 ethyl. Anyways, let's scroll down. Oh, I think these are actually the same problems we just went through. Hey, look at that. Yeah, these are actually the same problems. Woo! How cool. How cool is that? So let's scroll down again. And I actually need to refill my coffee. So I think what I'm going to do is take maybe like a 10 or 15 minute break. Refill coffee, get a snack or something. And then I'll be back on. I'm not going to shut down the stream. I'm just going to put up a little waiting thing. Picture overlay. Break time. Does a rotating thing fit in there? Oh, it kind of cuts out the clock. That's okay. I like the rotating molecule better than I like the clock. Okay, break time sound good for y'all? It's been about an hour and a half. I don't know, it's been about an hour actually. Okay. So I'll be back on about like 8:25 ish. Yeah, sounds good. Alrighty. Got my fresh cup of coffee. Oh, that's the wrong thing. I'm ready to go when y'all are, or if y'all are still here. I don't think I was actually gone for that long. Next time I'll have an actual like break schedule. I think that would be very useful rather than just taking random breaks, being disruptive and whatnot. Cool. Okay. So let's carry on, and I think I like this blue color. Gotta color it up, you know. Warm coffee is good. Okay. So let's get my. I just chose a blue color, and I'm gonna go back to my highlighter. Y'all know how this goes, right? Partial credit for intermediate products. Put your major product or reagent in the box. That's cool. So let's do this, right? Right, so this first reaction, H2SO4, and some heat. Do I still have the music on? I actually don't know. No, I do not. Good. Right, H2SO4 and some heat. We're gonna protonate this. And that's gonna leave a carbocation. Right, and then gotta look out for those rearrangements. That's gonna go ahead and rearrange. So you get the carbocation here. And then it'll eliminate to give you your Zaitsev product, right? Your most substituted product. So this should actually leave you with that compound. Look at that. First question on the reaction section, and it already involves a carbocation rearrangement. Pretty cool. Alrighty. So that's right. First step. Second step. KMNO4, warm concentrated. Right. We're going to be cleaving some double bonds. We got those ones in the middle there. So I'm going to use my handy dandy super secret trick and just kind of extend those out. Now usually I would draw it straight down like that, but if I erase the line, it'll just erase the whole thing. But I'm gonna have two little ketones there, right? Yeah. Right. I don't have any more. If I had more hydrogens to oxidize, I would further oxidize it. But I don't, right? I just leave it as a ketone. And then sodium borohydride. Don't know if y'all have learned that yet, but probably, right? So it's just reduction. Right, so that'll take your ketones to an alcohol. To two OHs. Just like that. Cleaves in the middle. Nope, I should probably actually draw that in the box. Not that it's going to be graded by anybody, but for the sake of completeness and whatnot. So did y'all learn about the ketones and aldehydes? Or not ketones and aldehydes. Your two reduction agents, right? Sodium borohydride and lithium aluminum hydride. Right, did y'all learn those yet in lecture? Or are you going to teach that on Tuesday? So I think in workshop we're going to do that on Tuesday. Kind of have to, right? That's chapter 11 stuff. She should have taught that in chapter 10, thinking about it. Right? 'Cause that's like formation of alcohols and whatnot. Anyways, it's a reduction, just how oxidation goes from an alcohol to like aldehydes and ketones and carboxylic acids. Your reduction agent will go backwards, right? So take a ketone, bring it back to an alcohol, take a carboxylic acid, bring it back to an alcohol, so on and so forth. Okay. So we have a thingy here, right? We have a nucleophile. Let's ignore the sodium. Who cares about sodium? We have a nucleophile. We have a leaving group and an electrophile here. Right? Benzene doesn't really care. I don't really care about it. But first step is just going to be SN2. Good old chapter 6. Right, so carbon here, that's that CH2. This carbon is that carbon. And then we have our triple bond. And then CH2, CH3. Right? Most common mistake on these types of problems, and let me do that in like a red or an orange, is don't forget that bond. Right, that's the most common mistake I see on these types of problems. It's just students kind of leave out that bond, and they draw this, and it's like, well, that's wrong, right? You're one carbon too short. Yeah, so don't forget that bond. Right, so second step, we have our Lindlar's catalyst. Very fancy. It's going to take we're adding H2 to our triple bond, right? Palladium's a solid surface catalyst. So the hydrogens will get added syn. And it won't react with a double bond that forms, right? So we'll stop at the double bond. Whoops. Let's draw a better hexagon, shall we? I'm pretty sure there's a hexagon tool, but that takes too long. Takes way too long, right? So let's see, let's do this right. Double bond there. And then ethyl. Right? Always count your carbons. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, good. I got 5 carbons as a substituent every single time. Okay, and then last step, MCPBA. We're going to take that double bond, make it into an epoxide. Now you might be tempted to change all these double bonds to epoxides. Don't. Or thing about benzene rings, if you know anything about them, is that they are very unreactive. So they'll just kind of stay the way it is. I don't know if Dr. B mentioned that explicitly in class, but you know, it's there. And I'm going to add my epoxide kind of the way Brandon does it, so it's easier. Like that. Alrighty. So not too shabby on the first two. The first one had that rearrangement, which was kind of cool, but kind of not cool, right? That's fine. Okay, let's carry on. All right, so first step here, we have hydrobromic acid. That's an acid. It's going to protonate our water, our alcohol, And then it's on a tertiary carbon, so that's going to go ahead and leave. Form as an intermediate product, form that. And then the only other thing we have in our solution is actually that bromine. So we'll be adding a bromine there. Right, so the Br minus, our conjugate base of the HBr, will come in and pick up the positive charge. Right, kind of like an SN1 type deal. Right, and that 0 degree C actually doesn't have the degrees, but 0 C kind of ensures that we won't get so much E1, not that that's an issue anyways, and ether just assures that it is that it won't react with anything else. Right, so this is just actually SN1. Or kind of SN1. I don't know, it's just straight up SN1, right? Protonation, leaving group. Yeah. Leaving group, carbocation, nucleophilic attack. Okay. Right, so we have magnesium and ether. So we're going to be forming a Grignard. MgBr. And then we're reacting that with ethyl acid chloride. I think that's what that's called, right? Something with 2 leaving groups on it. Right, that's the important thing. Is something with 2 leaving groups on it. So I'm going to draw this in like 2 different colors so it's easy to see. Right, so the original compound is going to be an orange. Right, so my little 2 carbons there, that's my orange bit. My new bond is going to be in pink, some hot pink. Right, I'm going to add it twice. It's going to attack first, come up, come back down, kick off the chlorine, and then your Grignard is going to react again. And then I'll draw the actual reagent that we're adding in blue. Right? So I'm adding like this little group right here. That's what's being added to the carbon. And then we're going to have another one right there. And then we have an alcohol to end with. How I wish we could actually have colored pencils on our test. It'd make it look so crazy. Okay, so that's the first page of reactions done. How y'all hanging on so far? What do y'all think? I'll take the silence as easiness. So this is easy. We can move on. Coffee. Okay, let's carry on. Alrighty. So for these reactions, BH3THF, we know that has like a second reaction that goes with it, and whoop, there it is right there. So let's just kind of make a mental note. These two go together. Right, so 1 and 2. Right, just anti-addition of an alcohol. Anti-mark addition, I should say. Right, so with regards to our compound, that'll form the alcohol right there. So the first reaction didn't have a hydride shift in the key. I would call bollocks. Yeah, I would call bollocks on that. I kind of have to be critical of what the keys say. Yeah, I would have to be critical of what the keys say on that. Sometimes they're like beforehand. I guess with this stuff over here, like they were totally right. Like this one, that should have been a no. So listen when your answer doesn't agree with them, kind of listen to see what they're saying. Why might that not be the case? Why is your answer wrong? But if you can just see that, well, like no, that totally should be like it forms a carbocation, right? So we should look for rearrangements. Then you should say like, okay, well maybe the key is just wrong here, right? Yeah, I would say there's definitely carbocation rearrangement there. It doesn't happen at the same time. Actually, so that would be the thing, right? So the way to determine that is, does this happen at same time? Right? Because if what could happen, and now I'm second guessing myself, which is dangerous. What could happen is the water just kind of hangs out there, and rather than forming a carbocation, the OSO minus, right? Because that's what does your elimination at the end of the day. Let's switch colors here so it's not so crowded. This could do more of an E2 type of deal and eliminate that, right? So if this happens more E2 like, then there's not really a carbocation. But if the carbocation forms, which it should because it's secondary and it's protonated, it should form. It should be able to form. Then there would be a shift. I don't know. I'll have to look at that and get back on that. Right, but that's the question, the answer. That would be the deciding question on that. Does the elimination happen more like E2 or does it happen more like an E1? Yeah. E2 or E1. Yeah. And I'm sure that would be like in your notes somewhere in chapter 8, I think. Or chapter 7. It would be chapter 7. Yeah. Anyways. Oh. Wait, he said not good. Uh-oh. Actually, I can whip out my I have my textbook right here, and I know that mechanism is right in my textbook. So let's look at it, shall we? While we ponder about what's going on. Formation of structure and synthesis of alkenes. That's what I'm looking for. Whole bunch of nomenclature. Not what I'm looking for. Physical properties. I'm looking. Is that it? No, that's just elimination. Still looking. That's the double elimination. Oh, that's with that iodine compound. Man. I don't know. Yeah, the book totally has a for acid catalyzed dehydration of alcohol. It has the water just leaving and forming a carbocation. Yeah, so yeah, you would have a carbocation formation. And therefore you would have the shift there. Right, so Wade has carbocation formation. Yeah. Cool. So we have scrutinized the key. It's a good start. Okay, let's move on to the next page. I think what I'm going to do is, like, I'm going to show a problem, and then let's see. Yeah, so I'll give you all a couple minutes to finish up this one, then I'll jump into it, right? Rather than just like me looking at it and jumping in right away. Yeah, I think that'd be better. Okay, so I did the first couple of steps, right? So the next step would just be sodium. And that does something. And then ethyl bromide. And that should give you your product there. Give you all a minute or so. Maybe 2 minutes. Let's see, what weird colors can I pick? I think I like this pink one. That's way too light. Yeah, there we go. Okay, so let's hop in here. Now, what on earth does sodium do? It's just straight up sodium metal, right? IP10 is like, it's a spectator ion, so go away with it. It's not, right? It's not an ion here. So I think I had this a couple of times on one of the worksheets, or a couple of the worksheets rather, where we use sodium just to deprotonate something. Right, and that's all it's going to do here. Oh, I've cut a carbon too short. Right, so it's just going to take off the hydrogen. Right, maybe the pink is just a little bit too bright, you know? Anyway, so here's a nucleophile. There's an electrophile. And there's a good leaving group. So let's go ahead and make that ether. O, and then just the two carbons from the ethyl bromide, just attached on there. I'm gonna switch colors. This is burning my eyeballs. Green, yeah, green's better. There's nothing wrong with the navy, right? Whatever. It's brighter than my future. It is very bright. Okay, let's go to this next one. I'm gonna do the same thing. I'll give y'all, I don't know, 90 seconds or so to look at it before I crack on with it. I just finished my second cup of coffee. That's an issue. halogenation? Yes, halogenation. It's a good first step. Absolutely. Just adding Br to 2 Brs, right? 2 of them. Bromine, bromine. The orientation doesn't really matter, but we know they're added trans, right? Because bromonium triangles and whatnot. Cool. And then what does the next one do? Right, so this is one of the 2 reactions that had a temperature definition. Right, so if you recall, this one is actually going to form a terminal triple bond. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. Right, so the first part of this will form it with a minus charge, and then we follow it with the acid. So we just protonate it again, get rid of that minus charge. Right, terminal triple, absolutely. And then that last step has the mercury in it. Now we know mercury from double bonds, right? Some mercury something forms like your Markovnikov alcohol. And what does that do with triple bonds, right? Because that's a double bond reaction. What if it's cold? That's a good question. So what if the second thing is cold, like at 0 degrees C or something like that? You wouldn't have enough. You'd be able to form your double bond, right? Actually, I don't even think you'd be able to do that. I don't think anything would happen. Yeah, I don't think anything would happen. If it's too cold, then you won't actually have enough, like the activation energy, to form your triple bond or even your double bond, because that bromine is there, affecting the electrophilicity and whatnot. So yeah, so if this is really, you only see it at one temperature, but if this is at a different temperature, anything colder, you won't have anything, right? So it says then anti-mark OH. That's a good first instinct to have, right? So as I said, like sidetracked. Now to make the OH, we're only going to use up one of the pi bonds, right? Just the same we did this, same way we did that. We only had one pi bond, so we just used it up. But for this, let's see. What? Oh, I switch back to the pen. There we go. 1, 2, 3, 4. There we go there. And then we have an OH here. We have a double bond. Right? But that's not going to be our final product. Right? So this is your enol form. And then the key thing here is that this is rather unstable under acidic conditions. Right? We have the sulfuric acid there. So this will actually tautomerize or tautomerize to be your keto form. So wherever the alcohol is, right? So we noted it was on the Markovnikov position. That pi bond is just kind of gonna move up in a way and form your keto form. But yeah, initially it's going to make the Markovnikov alcohol, just the same way that the alkene reaction went. This time it's going to react further, so to speak. Okay. So let's carry on. Let's see. Oh, there we go. So we're gonna be choosing the things to react with, right? It's like a mini synthesis problem. Wonderful. So let's notice a couple of things. One, let's notice stereochemistry. That alcohol and that cyanide are opposite chiralities, which is cool. Also, we're probably going to be using a CN minus somewhere on a bromine to get that. So let's take this a step back. Actually, I'll let y'all think about it for a bit. I'll follow what I said. All right, let's take this a step. Oh, no. I'll give y'all a couple of minutes to work on it while I try to sip my coffee. I actually poured it straight from the pot as black coffee. I wanted to see how it tasted. I think I'm going to be regretting it, but we'll see. It's very hot. Oh, very bitter. Okay. So this, believe it or not, is a two-step reaction. Right? So the first step is to use that the tosylate thingy. TSCL. Okay, so you mentioned dehydration. Okay, so let's do a quick, kind of like insert a page. Insert. Yes. Okay, now if I scroll, okay, that inserted a page above. Maybe I should actually just zoom out. Oh gosh. Hold on. I want to move this page forward. Can I do that? Move page down. Yay! Okay, so if I were to take this OH, right, now I were to dehydrate it, I'd form like that, right? In doing this process, I've lost my stereochemistry. Right? There's no way for me to react anything with this to give an R or an S product. Right? Like as soon as I, like with HBr to put a good group on there, my bromine doesn't have any stereo specifications. Right? I can't say this is R or S. And we're specifying over here that we want a specific stereo product. Right? So dehydration, it might be able to get you the bromine on there, which is very useful for that cyanide. But we need to retain stereochemistry, right? So SN2 works. It obviously doesn't retain stereochemistry, but if you react a stereo-specific compound, it'll give you a stereo-specific compound. It might not be the same, but you won't get a racemic mixture, right? And that's the important thing. And there are some reactions like this tosylate thingy. If I zoom in back here, so what this will do is it'll actually give you that like fantastic leaving group, that we've seen before. And it'll retain the stereochemistry that it reacted with. Right, so the big kicker there is that this retains stereochemistry between there and there. Right, and if we take this in here and just react it with NaCN, right, sodium cyanide, we have a very good leaving group. We have a secondary carbon. This is kind of setting us up in a strong nucleophile, so we're setting ourselves up for SN2. Right, we're going to replace the OTOS with the cyanide, and because it's SN2, we're going to invert our stereochemistry, which is exactly what we want. Yeah, that's exactly what we want. She doesn't show you this in class, but I learned the mechanism after I took the class. But do you want to see a mechanism for this reaction? Just by curiosity. Just to kind of understand what on earth that compound is. Because that was always like the hardest part for me when I was trying to remember these things is like TSCl. That's such a weird thing. Like, what on earth is that? how am I supposed to like remember that if it's just some obscure compound that I only used in a very specific scenario, right? And somehow learning the mechanism just added some value to that. Cool. Okay, so let's go through. Oh, I can leave it right here. And actually, from this, you'll actually be able to see why it retains the stereochemistry. Okay, so let's see. Let's say I have like this alcohol again. I know it's not the same exact compound, but you know it'll suit the purpose. So TSCl, right? This is actually, so the T stands for like T-butyl or something like that. It is the OTOS group. So if you remember, OTOS stood for this. It was T-butyl phenyl ring. That's like the OT. Oxygen S. And then, oh no, hold on. It was phenyl sulfur. We need like a sulfate. O and then R, right? So this was the rest of your compound. This is that really good leaving group, right? TSCl is that exact same compound. Except instead of the oxygen here, we have a chlorine. A good leaving group. Right, so this is OTOS, and this is TSCl. I don't know what happened to the oxygens. Actually, no, what happened to the O? I don't know why it's not OTSCl. I have no idea, but they decided to do that. There are other forms of this. I remember when I did undergraduate research, I mess with that a lot. Methyl sulfonyl chloride, which was just, instead of a benzene ring and a T-butyl group, it was just a methyl and a chloride. Right? And it was the exact same thing. It was just an easy way to add a pretty good leaving group on stuff. Right? But that back end of carbons, it doesn't really matter at all. I think TSCl is just kind of cheap, and that's why we use it a lot. Right, so let's draw this out, and then we can start to look at a a mechanism okay. So actually, I guess we don't have to go through the whole mechanism for this. We can just kind of identify stuff, leave it at that. Because I just realized, so this is SD5 hybridized, right? It has 6 bonds on it. And in my head, I was thinking, actually, we can kind of summarize the reaction to be this. Let's use the pink again, right? Essentially like this. That attacks the sulfur. That kicks back up, and exactly like your Grignard. Actually, let's redraw it, but not in pink. Right, so now we've formed a bond, and this is probably why Dr. Bean didn't go over how this happens in lecture. Thinking about it. O minus, double bond O, Cl, and then the rest of this mess. Right? Now, just like your Grignard reaction, well, kind of just like it, right? But we have a good leaving group on that sulfur, so this can go back down and kick off the sulfur. Right? And I'm pretty sure this is not actually the way it happens, but it's a good way to think about it. It gives you the same result. Oh, and of course that is positively charged. And then we can use the chlorine afterwards to pick off the hydrogen. That's fine. Oh, and I've forgotten the rest of my compound. There we go. OH plus S, double bond. We just reformed that double bond. O. There we go. And notice what we formed here actually after we do the deprotonation. More pink. More pink is required. Let's just go through that. There we go. And that stays on a wedge. So this is kind of one of the important notes that I want to make. So now we've formed our tosylate group. And notice here, the O branching off of your substrate of the tosylate group is actually the alcohol that was on your compound, right? That's why it retains the stereochemistry, because this alcohol never gets replaced. It stays there. Let's make that an aquamarine. That's too dull. No, yeah, that's fine. Right? In all of these cases, our wedge O never gets changed. It gets protonated and deprotonated and stuff like that, but it never gets changed, right? So there's no reason for the stereochemistry of it to change, which is why it retains it. And our tosylate, afterwards we formed a tosylate, that O is part of our tosylate, which we formed there. There's the tosylate. Right? Now, again, it doesn't really matter what else is on there, but the fact that the O stays where it is, retains its stereochemistry, and now we've made that O essentially a really good leaving group. That's what's important about this reaction. See if I can get it all on one screen. Yeah, about there. Okay, did that make any sense? Like the key points of that. I really like the pink for mechanism, for electrons. It really makes it stand out. As a little side note. Kinda. Indeed. I think this is in Orgo 1, actually in Orgo at UH, we kind of skip thiols. Um, as a like I said, we kind of the textbook goes over a lot of material, right? And there's a lot of stuff going on, and the course is already full as it is. So we actually skip the thiol section completely, and we just kind of move on to alcohols. So if you want to learn more, you can probably read about it in the thiol section. But I think that's why Dr. Bean omits this mechanism and how this works, is because suddenly we're dealing with SD5 compounds and it's weird. But as kind of a summary, let's see if I can switch back to that pink. Oh, in a pen. Yeah. This alcohol is that alcohol. Or that the oxygen is that oxygen. Right? You just have to remember I need some sort of sulfate with a chlorine attached to it. Right? It's TSCl. Okay, let's move on to the next page. Oh, it's a mechanism. Okay, I'm gonna leave this up while I put some cream and sugar in my coffee because I can't drink black coffee. So I'll be right back. It'll just take me like a minute or two. Y'all give a shot at this mechanism. Okay, I'm back. Any luck? Apparently, black coffee doesn't taste bad if you have good coffee. Apparently, I always have bad coffee. So I've read on the interwebs. Is this a Markovnikov reaction? Absolutely, it is. Right? We have just HCl and a double bond, and we're like adding more of the compound to it. Dude, how does that happen? We're not even adding a chlorine. Mechanism are not my forte. Okay. Well, let's use the pink pen for arrow pushing. Right? So right away, we can tell. Actually, I'm going to not use the pink because I'm not going to do mechanism yet. Now that hydrogen is slightly positive, and that double bond's a nucleophile, right? So that can attach that, or attack that, and so one of these two carbons. I keep bringing out that drawer. There we go. So one of these two carbons is going to get a hydrogen, and can I give us like 5 minutes? Yeah, absolutely. Yeah, go for it. Sorry, there's a bit of a delay between like the time that you chat and the time that I see it. Well, here, I'll go kind of slow. So if you're trying to do it yourself, try to stay a step ahead. Right. Yes, so the double bond is a nucleophile. Absolutely. Right? Remember, what defines a nucleophile is just a thing or an area with electron density. And your double bond is definitely a place of electron density. Right? So yeah, so your double bond is your nucleophile. So one of these two, when the double bond attaches, hydrogen can only take one bond, right? So one of the carbons is gonna have a hydrogen added to it, and the other one is gonna have the carbocation, right? So we need to determine which carbon gets what, and the thing that can hold the carbocation better is going to be the thing that gets it. So you're more stable intermediate, so to speak. Right? So in this case, we have the decision between a primary carbon and a secondary carbon. Your secondary carbon is going to get the carbocation. Right, so that gets a hydrogen. This gets a carbocation. Cool. Now, kind of looking at what we're trying to form, we definitely don't add that chlorine back on, right? So I'm just going to ignore that chlorine until maybe the end to form back that double bond. Possibly need it for some sort of elimination, but we can worry about that later. Right? But for now, I'm left with a carbocation. So I have to ask myself, do I have a more stable spot for that carbocation? Good. So I think, okay, well, this is a secondary carbon. If I go to the left, that's primary. That's not good. If I go to the right, that's primary. That's not good. If I go to the left, this is tertiary, and I definitely have a hydrogen there. So I can do a hydride shift. Whoop. Go back to pink. I wish I had a hotkey for that. There's probably a way to set that up. Right, so I just do a little hydride shift. So the hydrogen is now here. I'm going to ignore that other hydrogen. It's still there, but I'm not going to write it. And the carbocation is now there. Cool. So now looking at this mess up here, this bond was formed between probably what I have down here and maybe another one of those, right? Because at this point, the compound that I have, I can't do any more work with it, right? It's tertiary, like it's just the way it is. So what I'm going to do is I'm going to bring in another one of these, right? Because I have this hanging around a solution. So it's completely possible for it to for my compound to bump into another like starting material, right? That's completely possible. So I'm gonna say, well, this is a nucleophile. Oh, let's switch back my pens. Orange, right? This is my nucleophile still. I definitely have a much better electrophile here, right? So same thing I did in the first step is I'm gonna make this attack here. Now it's gonna get a bit messy, but that's okay, right? Same thing I did here. My secondary carbon is going to get my carbocation. So this one's going to get the carbocation. And my primary one is going to get the bond to the rest of this compound. So let's see if I can do it in different colors, right? So in purple, I'm going to draw out this compound just to kind of keep them separated in my head. So I'm going to draw back there. That and that. I know that gets a carbocation. And this is the new bond that's formed. And I know it's formed at the base of the other cyclohexane, right? Because that's where the nucleophile, that's where my double bond attacked. Just like that. Right, so pretty much exactly the same as the first step, except with something a little more complicated than the hydrogen. Right, so here we're left with another carbocation next to a tertiary carbon. So let's go ahead and do that. Have that hydrogen there. Now you could actually, at this step, you could just eliminate to give this double bond. Right, use the chlorine and eliminate to give your double bond there. Yeah, I would just do that, actually. I was going to say, do the hydride shift and then do that, but what is more correct? I would say to do the hydride shift would be more correct. And then you're going to end up doing the elimination to forming the same product anyways. But that's okay. Positive charge there. I've not drawn my electrons yet. That's bad form. So these just move over here. That's fine. So the hydrogen moves, and I'm going to eliminate it on this step, actually. So I have, whoop, don't want to do that in pink. Green, sure. Hydrogen. I'm going to use some base in my solution. The only one I think I have actually is the Cl- that I deprotonated in the first step. So that is going to swing around, grab that hydrogen, and form that double bond. And that's product. That's it. Can you assume it's in water? Yeah, I think so. I would kind of, Can you assume that it's in water? I'm going to say no. Just because if this was in water, no, yeah, I would say not to assume that it's in water because it's not specified right here that you're in water, because you could very well carry out this reaction in ether and actually probably be better, right? Because your starting material is not soluble in water at all, right? So if you tried to do this reaction in water, it actually probably wouldn't work. Then again, hydrochloric acid is usually an aqueous solution. So maybe? But I would try to make as little assumptions as possible in that, right? In fact, some professor, I don't know if Dr. Bean thinks this is okay to do, but I mean, it's going to be Cl minus to do the deprotonation here. It could be like another starting material starting off, like instead of deprotonating the hydrogen from the chlorine, it could do this deprotonation to start off the reaction, right? That could also work. And there's probably something else that I'm missing that you could assume does that deprotonation. But anyway, some professors actually just prefer to use a B for any old base because there's some base there. Could you reiterate what happened to the double bond on the lower left corner? Lower left corner, yeah. So let's switch to a different color. There are many other colors, you know. This green works. Yeah. Actually, I probably should use highlighter. Yeah, there we go. Okay, so this bond right here is basically acting as a nucleophile, right? So, and we had an electrophile that we just made, right? So just the same way the nucleophile up here attacked, or a double bond up here attacked that hydrogen because it was an electrophile, this double bond in the lower left-hand corner is going to attack our carbocation because it's an electrophile, right? And then the same kind of thing happened, right? So to start off with, we added the hydrogen, the electrophile, to like the primary carbon, and then the carbocation went to the secondary carbon. Well, here we added, or we're not adding a hydrogen, we're adding this other, you know, big thing. So we added this big thing to the primary carbon, and the carbocation went on the secondary carbon of that. Does that make sense, or do I need to explain that again? And Quinn, how'd you do? Did you get it? Oh, my coffee is so much better. Cool. You're welcome. Okay. So let's carry on. Well, can I like zoom out? Is that possible still? Oh, we're at the bottom of the exam. Oh, last question. Just a synthesis. Just a synthesis, right? Okay, so it says synthesize the molecule from alkanes, alkynes, or alcohol. So we have a bit of leeway here, right? We don't have to just start from alkanes. Of 3 carbons or less, and any inorganic reagents. This ain't too bad. I've always hated the way that she writes out these compounds, though. Just write them in line angle notation. It makes them so much easier to see. 1, 2, 3. It's so much easier to look at. I don't know. Actually, looking at it, it's not actually that much easier to look at. Maybe there's a reason why she writes it like that, right? Okay. Any thoughts? Do we have any techniques that we can possibly use? Cleave the triple bond. Like just right here. Are you going forwards or backwards? Remember, we want to react something to form that, right? We don't want to, like, we don't have this compound yet, right? We don't we don't want to do that. Yeah, I'll give y'all a couple of minutes to work on it, right? This is the last problem. But yeah, if you have any thoughts on how to start, then you can post them in chat, and I'll give you what I think about it. Because there's a couple ways you can start with this. Greenyard, okay. Okay. That's a good way to start. Well, maybe you just sparked some thought into somebody else, you know? So we can't use the triple bond carbon thing because that's a secondary alcohol. Triple bond carbon thing. I think I'm gonna I think I'm gonna have to ask you to elaborate a little bit on that. Triple bond carbon thing. Like an acetylide ion? Maybe. Yeah. If you have any thoughts, just write it down somewhere. So try it out for yourself. I see. I think that's as close as I can get. See the line. You could actually use the acetylide ion for this. Yeah, there's a way to work that. In fact, you kind of have to, in a way. But like I said, there's a lot of ways to do this. You can probably get away with like explicitly using Greenyard. But yeah, using acetylide would actually make your life a little bit easier. Okay, so so I'm gonna tell y'all what my eye is directly drawn to. My eye is directly drawn to that alcohol. And that acetylide, because I know that this whole group right here can be, actually that front carbon can be a nucleophile, right, with the acetylide ion. And if I look here, I have an alpha substituted alcohol. right? So if you recall from when I was telling you on lecture, or not in lecture, in workshop, is if you have alpha substituted alcohols, you can start from a ketone or aldehyde, something like that, right? So long as you know what your nucleophile is. So I'm going to actually highlight 2 parts of my compound. I've already highlighted one part in orange. The other part is going to be the substrate that has my ketone. Right, so I have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, so 5 lines. And I have my alcohol on the 3rd carbon. So I'm going to have my ketone here. And I'm going to have my acetylide. 1, 2, 3. 1, 2, 3. There. Right, and then I have to follow that up, right? Because this will give me the O- after that nucleophilic attack. So I have to follow it up by then H3O plus to protonate it and give us the alcohol. Right, so that's how I would start that off. Look for that alcohol and see if I can tell if it's alpha or beta substituted. Yeah, the hardest part with these problems is where on earth to start. And just that one identification can help. Right, so in her notes it says only primary methyl and secondary tertiary will be E2. So you're saying if I react a ketone, I'll get an E2? I don't think so. Maybe if I had a bromine. Right, I totally agree if I had that bromine. And the acetylide, I get an E2 reaction, but I don't. Right, I have a ketone here. Yeah, you can do that, right? The carbon on the ketone is very electrophilic. And in fact, this happens the same way a Grignard does, right? Just the same way a Grignard will react with a ketone. Your acetylide will also react with a ketone because it's an electrophile. Okay. So now let's look back, right? So we can start with 3 carbons or less. Neither of these 2 things are 3 carbons or less. This is, if I split that right there, that's in chunks of 3 carbons. So that's cool. And if I split that right there, that's in a chunk of 2 and 3 carbons, right? So I kind of have a headway, but I still have to make a couple of carbon-carbon bonds. So on the let's work the left-hand side first, right? Because it has more to do with alcohols and stuff like that. So I want to form a ketone, and I know that I can use alcohols in synthesis really usefully, right? Really useful. Does that make any sense? Alcohols are useful for synthesis because they give you such good insight on how to form your compound, right? So if only there was a way that I can take an alcohol and react that to give a ketone, right? That would be super useful. So, well, it just so happens that there is a way to do that. Right. So here I would use some sort of oxidation reagent. I think this is either in. I think this is in chapter 11. So she may have taught it already, or it might be soon to come on Tuesday. But I can use any sort of oxidation reagent. I'm going to use Jones. I could have also used PCC. I could use potassium permanganate. I could have used sodium dichromate. Cr2O7. Any one of those would have worked to form that ketone. Okay, so let's do the same type of analysis I have here. Now I want to split this up in like 2 or 3 carbons, right? I have 6 carbons here, so if I split it up into 2 groups of 3, then that works out brilliantly. So if I make that one group, and I make this, oh, it's really dark, this my other group, I notice, oh, can I switch to my pen? Thank you. I notice that, again, my alcohol is alpha substituted, right? So I'm going to be starting with, don't want to do that. Only bad thing about using colors is you have to constantly switch. There we go. So I'm going to be starting with an aldehyde this time. And for the left-hand side, I'm not going to be using, I could use a triple bond again, but that won't form my thing directly. It's kind of a pain. What I could use instead is actually my Grignard. Right, so MgBr plus that will yield that, right? But then I have to use then H3O plus again. Right? Okay, so now I have them, my 2 compounds, the correct carbon length, which is perfect. Now I just have to get these back to alkanes. What was I allowed to start with? Alkanes, alkynes, or alcohols. That's what I was allowed to start with. So let's bring this right-hand one down to an alcohol. Right? And again, I don't know if Dr. Bean has taught over this oxidation yet, but to get your aldehyde and the stop oxidation out in aldehyde, the only reagent we know to use is PCC. That'll give you your aldehyde. And we can stop at 1 propanol. It's a 3-carbon chain and it's an alcohol. Right? And then for the bromide, or for the propyl magnesium bromide, Mg ether. Oh, this might be a little tricky, right? Because here we have we can't just use Br2 and light here. Won't give us the right product. But if we use HBr and peroxide, we can start with that alkene. Right, and we're allowed to start with alkenes. So that's good. Cool. I'm just double checking my work to make sure I didn't make any mistakes, and I think we're good. Right? So let's get, I think I have like a stamp. Yes. Check. Check. I can start with that. Okay, so let's do the right-hand side. Okay, so let's look at this. So part of me wants to like form that terminal triple bond like right away. But actually that's going to be kind of useful for me. Because I still need to form like that bond right there. So if I kept that triple bond, I can use the acetylide ion kind of twice. We'll have to label them as excess. I don't think so. Not the HBr. I think we only did that if we needed the Br2 in light. Right, Br2 in light in excess, so that we only get monobromination. But yeah, for HBr and peroxide with a double bond, I don't think you need excess, but I'll have to double check that. Okay. So anyways, back to this. So I don't want to get rid of my triple bond yet, or get rid of it or form it right away. Instead, what I'm going to do, I've just erased a thing. NaNH2 is I'm going to take it back to something that's protonated, and then I'm going to make the bond on the other side of the triple bond. So I'm going to make this bond now. With the acetylide ion. Right, so the acetylide is going to be my nucleophile, and then 1, 2, 3 carbons with the bromine is my nucleophile, right? And that's primary bromine, acetylide to acetylide, so that will give me complete SN2, no E2, no risk of E2 happening, and that'll work fine. Right, so best thing about the compound here on our right is that we've already made it. Smiley face. Right, we made it over here. It's the exact same compound. I'll just make a little side note over there. Right, that's the exact same compound. So we don't have to, do double work, even though it's just one reaction. And the last thing we have to do here is just, we're allowed to start with alkynes. So we can start with that triple bond. And use that to get the ion. Right, and we're allowed to start with triple bonds of 2 carbons or less. Or 3 carbons or less. And that's it. I think we're all good. Okay, so like I said before, these have a million different ways to do it. Some are, I remember, words. I remember when I took the course, my mechanisms were always super, super long because I would continuously make not the best decision on where to split my compound every time. And I'd kind of have to like double up on the work just to get it fixed, so to speak. But anyway, so if you have a different way to do it, feel free to send it to me or show it to me during workshops, something like that, and I'll make sure it's okay to do. Yeah, because there's just a lot of ways. Like, this is definitely not the only way to do it. Yep. In fact, that might be a good challenge to do. Is to think of a different way to do it. But yeah, maybe a different way to split it up to begin with. Okay, well, let me check the drive and see if anybody else came in with any questions. Doing the test Took a lot of time, but it's okay. It was good. We don't really get the opportunity to go through a whole test and workshop. I wonder what the key had for this. Yep. Okay, this is interesting. So if I bring up the key for it, right? So for the mechanism bit, I don't know if y'all can see my cursor or how well that's coming up on the thing. So if you recall on this last step here, we had done the hydride shift before the elimination, but the key just has the elimination to form the double bond, and that's perfectly fine. On the synthesis, it looks like they made the same choice that we did. Wow, it looks like they actually did the exact same the exact same synthesis route that we took. Even down to Jones, right? Jones there. They use PBr3 to take this back to an alcohol, but what we have is perfectly fine, right? Yeah, that's perfectly fine. Cool. And just to double check the nomenclature at the beginning. This looks like different nomenclature. Do we have this? I think we're missing that double bond there. I don't remember that double bond being there. Let's flip back. Should be at the top. Not that it matters at all. But it's interesting. Yeah, our thing didn't have that double bond there. That would have changed our answer, wouldn't it have? Okay, well that's cool. Let's look at this again. And then, right, yeah, so it's 6-ethylphenyl and 2,3-butynyl, or however you pronounce that. Is that what we had? Oh, yeah, that's pretty much what we had. Cool. Yeah. So I think that's all I'm going to be doing tonight. It's approaching 10 o'clock. I'll get this posted on Blackboard and whatnot. And, I'll see y'all on Tuesday. Let me know if this is helpful or not. I might have one before your final. Not like Thanksgiving break, but the week after that. So 2 weeks from now. Cool. Let's get this thing. Let's exit out of here. Let's save. Overwrite. Yep. Do. Sometimes it's just quicker to type in the chat. Yes, just so y'all can get a glimpse at like how bad the delay is. So, see you Tuesday! Exclamation point. I'm gonna hit send, and yeah. helpful, but you can test. I actually don't know which test I'm going to do. This was just posted to the Google Drive. Um, so yeah, I don't have any prepared material for this. It's just things that people post in the Drive and whatnot. Um, yeah. Do, 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 do. Goodbye. Good night. So long. Farewell. Ask we just saying goodbye. No? No. I need to listen to that song. Oh, I should probably stop the string or something like that, right?